Hello everyone, hope you guys are doing good. So today we are going to change the topic and start a new type of mechanism with what we call gears and gear trains. Remember we said something about the definition of mechanisms, and in that we said that we're going to provide the input in a specific way, and the mechanism is going to transform that input into a motion which is desirable, which is of a specific kind. Specific in a sense that it performs the position displacement, the velocity, as well as acceleration, and in certain cases jerk as well, in a very precise, specific way. And that's exactly what gears and gear trains are going to do as well. They are going to receive the input and then transform that input into a specific output which performs the job for that machine. And you should also realize that this whole journey, should I say, started from linkage mechanisms, and we performed quite a few details in that. There were quite a few linkages that we investigated, and from there we moved on to cam and follower mechanisms, and from there we are shifting now to gears and gear trains. So the basic idea is repeated again and again. We're going to provide the input. Let me use a different color to the linkage, and the output is going to be received out of that in a specific way. So this is going to be desired output, and this is going to be the input which is available. So for a given input, the desired output is achieved using this specific way of placing the linkages, cam followers, gears and gear trains. And that's why it is in that continuation of the same topic under mechanisms. And I should also emphasize that gears are going to have quite complex geometry associated with them. And for that reason, we're going to discuss the construction details as well. So this particular lecture is going to be the introductory lecture for the gears and how we construct them, what are the different types associated with them. And then in the next lecture, we are going to cover the gear trains. So let's start the journey. So whenever we start a new discussion, we raise this question: why do we use, or why do we need that? So in case of gears as well, we're going to rationalize once again the reason for which we use the gears. So the primary reason is to reduce or increase the speed of rotation, because generally the gears are going to be rotational elements. If it is a rack and pinion, that's the exception. We are going to discuss briefly that as well. But generally, reduction or increasing the speed of rotation is going to be a reason of using the gears. Not only that, with the reduction in speed, you may have the possibility of increasing the torque of rotation, and by increasing the speed, you may reduce the torque as well. So this is something like at the expense of speed, you can have the torque increased. So with this kind of arrangement or mutual correspondence between speed and torque, you can have the use of gear trains. And then if the requirement is to transmit power by changing directions, for example, in order to allow transmission around corners, or to cover distances in order to have input on one side and output somewhat distanced from the input, you can use the gears. And not only that, you need to have some sort of other aspects of transmission to be considered as well. For example, you may need to have the efficiency considered for the transmission as well. For example, if you provide the input, how efficiently or how reliably it is transmitted to the output, that is going to be an important consideration to have. So that may have uh, a direct bearing on selecting these kinds of gear profiles. Accuracy is also an important aspect to be considered, and also the smoothness, the reduction in noise, the reduction in vibrations while transmitting is going to be an important set of considerations as well. So in nutshell, I can say that primarily we are going to have speed and torque to be correlated, and that's why we're going to use gears or gear trains, but also because of transmission around corners and over distances, these are going to be possible choices, and also because of the other considerations of transmission in terms of efficiency, reliability, accuracy, smoothness, and vibrations as well. These aspects are going to be also making us think that probably the gear trains are going to be suitable options for such mechanisms. So let's first study different types of gears that are possible. The very first type of gear that we should start our discussion with is called spur gear. Now, if you observe very closely, there is going to be the axis of the shaft on which this gear is going to be mounted like this, and the gear teeth are just like in parallel to this axis line. You can observe over here, you can observe over here, and you can observe corresponding to this center that the teeth are structured in a specific way that are parallel to the axis of rotation. So if you have that distinctive feature in the gears, you would call those to be the spur gears. Now the other type of gears is what we call helical gears, and these have been shown in the second figure just flashed in front of you, and you can see that appearing like in a helical fashion. For example, if I just try to draw it over here, that would be something like you have the axis of rotation like this for this particular uh, gear, and if I use a red color over here, this follows a helical line like this. So this gear tooth is exactly following some portion of the helix, and that's why it is called helical gear. So you can use the helical gear to transmit power from one side to the other side. It is also possible or likely to change the direction as well. So these are the second kind of gears. The third kind of gears are called worm gears. And you can see that like over here there is this worm profile. Actually, I should start with a axis of rotation around which this worm is going to have a rotation just like a screw. And you have uh, some mating gear which is like engaged with this worm outwards over here, which is going to have a rotation about this axis. Now you can see that obviously the direction of rotation is changing. The axis of angle, the axis of the gears are indicating that. But you can also observe that it is a bit differently structured as compared to the helical gears that you have seen previously. The fourth type is what we call bevel gears. Bevel because they correspond to the truncated cone like this, out of which the gear profile has been carved out. Now, uh, you can see that input side and output sides are in different directions. So that's one advantage that you can get. Also, there are some other auxiliary advantages that we're going to discuss in much more detail later on. But at this particular stage, the idea is just to give you the possibilities of having the axis of rotation to be in parallel to the teeth, uh, in parallel as well as along different directions in case of helical, and in case of worm, different kind of structural arrangement, and in case of bevel, a different kind of structural arrangement to allow the effective use of transmission from one side to the other possible in different ways. And generally what happens is that the following three, the helical, worm, and bevel gears are generally when we don't have the parallel shafts. When you have non-parallel shafts, you can use these options. Now, type of gears is the identification of different types of gears is fine, but at this particular stage, we should also realize, because you can see quite a few gears in front of you at this moment, uh, what is going to be the standards corresponding to this wide range of possibilities. Whenever you have some sort of machine component to be designed, there are always standard ways of doing that, whether be it screws or nuts and bolts and or fasteners or some other elements like joints and links and all that. Similarly over here as well, you need to follow standards in order to make them according to the requirements. And there are quite a few organizations which do provide you with standards, and the one that is most commonly used is American Gear Manufacturing Association, AGMA, and there are quite a few standards defined by them in order to define some standardized ways of manufacturing these gears, meeting closed tolerances and meeting the performance criterias corresponding to these. So what you're going to do as a little exercise, you are going to study AGMA 6 and AGMA 7 standards, and you're going to try to comment on that what is the difference between when you say that one set of gears is compliant with the AGMA 6 and the other set is compliant with AGMA 7. What is the difference in terms of quality that you have to identify as a little exercise in your notebooks? So at this particular stage, we have just presented all the four types that we are going to discuss in much more detail in the subsequent slides. Now, in case of spur gears, we have mentioned that you are going to have the axis of rotation. And this axis of rotation for this gear is going to be something like this, about which the rotation is going to happen. Now, the salient feature of the geometry of spur gears is that the teeth are going to be in parallel to the axis of rotation. So that's the kind of distinctive feature, and that's right indicated over here. This is going to allow you to work on parallel shafts. So when you have the input gear to be a spur gear, the output gear is also going to be a spur gear, and that's why the parallel shafts are going to be the necessary feature. Now, I should take a step back and make you see that what is the ultimate objective of having the gears. It is to transmit torque as well as the angular velocity from one side, from the input side to the output side. And that's exactly what it has to do. And when we compare it with these simple rolling cylinders, it is going to be much more efficient. So that's the selling point over here for opting for spur gears. The kind of description of this one would be something like you have a rolling cylinder like this, for example, and you have another rolling cylinder just like on the same line over here. You have another cylinder. So the axis of the first one is like this, the axis of the second one is like this, and this is the surface which is going to be in contact with each other. Now there is this necessary condition over here that you need not to have any slip over here. No slip condition is required, which is not always guaranteed when you have a simple rolling operation. So that's why it is going to be somewhat problematic when you have pure rolling cylinders. You cannot really guarantee that there is not going to be any slip. But alternatively, if you use spur gears, you are going to almost guarantee that there is not going to be any slip associated with this kind of arrangement. So that's the second selling point, that it is going to be relatively much more efficient than the simple rolling cylinders. Now, you need to also realize that there can be multiple different possibilities. The one that is going to be remarkably different from general spur gears is the rack and pinion mechanism. Now, the difference is that you have the rotation happening on this side, which is the pinion, and the rack is going to have the linear motion. You can assume that the rack has got the radius to be of infinite length, and that's why it is just like a straight line. Uh, so in order to kind of remain consistent with the previous discussion, you can assume that. Uh, and that's one very interesting application where you can see that the rotary action can be translated into a linear action, or a linear action alternatively can have the rotary action, depending upon the direction of motion being imparted. So with this kind of versatility associated with spur gears, and with this kind of simplicity of construction, it is very commonly used in toys, in watches, in printers, etc., in car steerings, in diving boards, etc. That you would be amazed that it is something like a very something like most commonly used type of gear trains. So I'm sure that you have already observed, or you've already experienced such kind of gears. Another aspect that I need to emphasize over here is corresponding to the selected material. Now, since you know that it is going to be the torque or the power being transmitted from the input side to the output side, it would be absolutely necessary to consider the material requirements. So depending upon the type of application, you can choose the metal spur gears, or you can use some plastic or polymeric spur gears as well. Sometimes nylon or some other composite material can also be used. So in terms of material possibilities, there can be different ways of opting for that. So I've mentioned like two, there can be multiple other methods as materials as well. So that can be added as well. Metals, plastics. Actually, the Delrin or Delrin 500 is most commonly used plastic spur gear. You can have for example, the nylons and composites as well. So there can be multiple ways you can have the material selected depending upon the type of uh, power transmission from one side to the other. So this is just like a very brief introduction of spur gears. We have not uh, introduced the machining process. We will probably do that in the subsequent slides. So the other type of gears is called helical gears. The term itself is coming from helix. So this is a derived word from the helix. And you can see that, for example, over here, if I just make you once again recall that we're going to have this as the axis of rotation, and about which you're going to have uh, a helix of this kind constructed. And because this tooth profile is following a helix, that's why these kind of gears are called helical gears. Uh, and obviously you can see that there is some sort of angle associated with this helix. For example, this can be possibly 45 degrees. And sometimes it is going to be a bit different angle as well. So the angle of helix is going to be possibly what is going to change the nature of these helical gears. The other possibility is, in order to change the way the helical gears are assembled together, is to determine the hand of gear. Now, what does that mean? It means that, for example, over here in this diagram, part A, you can see that the direction or the hand of the helical profile is going this way, and for the lower gear, it is going the opposite way. So if these two are going to be opposing each other, that is going to be called opposite hand pair. And generally, this opposite hand pair is used when you have parallel shafts. So if these two shafts are going to have parallel uh, orientation, you're going to have the opposite hand pair used for that kind of arrangement. But sometimes or oftentimes you may not require the parallel shafts to be assembled together. You need to change the direction of rotation from one axis to the other axis. For example, over here in case of B, you can see that for the lower gear, the axis is coming out of the screen, and the other axis is going parallel to the screen, something like that. So these two are probably mutually orthogonal or 90 degrees apart from each other. And in this case, you can see the direction of helix is something like going this way, and the same type of hand is being used for the lower gear as well. It goes similarly this way as well. So uh, because of that, this is called same hand pair arrangement for the helical gears. So this is going to kind of make you arrange these helical gears in different possible ways in order to change the direction. Remember, we started our discussion by saying that one of the best advantages to use gears is to, like, you can change the direction from one side to the other, and that's exactly what is possible by using helical gears. It can do the parallel transmission. It can do transmission at 90 degrees apart angles. So with this realization that you can have the opposite as well as the same hand pairs, you can have different orientations. The other aspect that you can kind of identify is to rationalize use of helical gears. So what happens is that as compared to the other spur gears, it has got the reduction in noise possible. And that's because of the nature of engagement of tooth profile with the mating tooth profile of the other gear. Because you have a different kind of arrangement, it allows you to have reduction in noise and vibration, and that's one good advantage to have. And because of these advantages, these are used in distributors and speedometers, and that's why these are one of the most commonly used gear profiles that you're going to encounter in practical life. Now, at this particular stage, I'll ask a question, and that question is going to be explored by you guys. And the question is that if one chooses helical gears for transmission, what additional requirements will be added for the bearings? Obviously, these are going to be mounted on shafts. Shafts may be mounted or supported by bearings. So if you use the helical gears, you can see the advantages, but what is going to happen to the bearings, or if there is any specific requirement for that. So you're going to explore that and answer me in the comment section later on. So the third type is called bevel gears. And if I just opt for this particular diagram, I would readily observe that the gear profile has been carved out of a beveled surface like this. Now, because this is a beveled surface, that's why these types of gears are called bevel gears. Now you can assume that the top cone has been truncated, like from top, and the remaining surface has been where you have carved out the gear profiles. And that's exactly what is at display over here. Now this is one of the gears. The other gear is also going to have a cone-like structure and possibly the truncated cone, and the point of intersection is going to be an important point of intersection because that should coincide right over here at this point. And this point is very much clear in this diagram. You can see that there are two cones getting engaged with each other, and the point that is important point that you have to make sure that these are coincidental. That is over here. Now, if these 2 points are not coinciding with each other, this is going to be the scenario, and this is where you have velocity mismatch. And this velocity mismatch is going to make this arrangement to be incorrect arrangement. So you need to make sure that whenever you have bevel gears to be machined and manufactured or assembled later on, you need to ensure that this point of intersection is properly taken care of. Now, the other thing that you can assume that you can observe is that the input side and the output side are spaced apart with this angular displacement gamma. And that's exactly because of the angle of these bevel gears. And this is the flexibility, this is the good thing that we may exploit while using the bevel gears, that you can have the input side and the output sides spaced apart at different angles. So coming back to this point, that you need to make sure that the previous gears, that the ones that we have previously mentioned, were coming from the analogy of mating cylinders, but this one is coming in from the mating cones concept. And that's what makes these bevel gears to be different. Now, what happens is that you need to make sure that sometimes it is going to be the straight gear profiles that you cut or carve out of these bevel gears, and sometimes this is going to be the spiral arrangement that you need to make sure that you need to arrange. And the difference between the two is that spiral bevel gears are going to run much more smoothly and quietly as compared to the straight counterparts. So you can see the two examples over here. This one is for the straight example, and this one corresponds to the spiral example. And obviously you can see the internal arrangement is quite different. And obviously the machining process is going to be significantly different from each other. And obviously spiral, as the shape is suggesting, the machining is going to have much more stronger stringent conditions associated with it. Now, as you have just mentioned that or just have seen that the spiral bevel gears are going to run much more smoothly and quietly as compared to straight, but this is in addition to the previous advantages being that you need to transmit force from one side or from one axis to the other axis, probably having a selectable gamma or the angle between the two axes as the biggest advantage. And on top of that, you can have a very effective way of force transmission. And on top of that, if you choose spiral bevel gears, you can run this operation much more smoothly and without noise. So at this particular stage, I should also realize that the differential arrangement in the automobiles is generally constructed out of these bevel gears because of these characteristics that we have just listed. Fourth type of gears is called worm gears. Worm gears are going to have two major components in it. One, the worm itself, and the other one is the worm gear. So the worm is being indicated in red like this screw structure that you have constructed out of a shaft. This is going to have two bearing surfaces, and the axis of rotation is going to be this, about which the rotation may happen. So when the worm is going to have a rotation, worm gear, which is also going to have an engagement at this particular place, it is going to have a rotation as well. But this is going to have a rotation about another axis, which is going to come in this orientation out of the screen. So you need to kind of realize that when worm is going to have a rotation about its own axis, you are going to have a rotation about another axis, which may be 90 degrees apart uh, with a different gear ratio. So For that reason, you can see that not only the worm gears are going to allow you to have transmission of torques from the input side to the output side, and also the corresponding angular velocities as well, it is going to have a change of direction also imparted as well. So with this realization that a worm gear is going to have two components which are going to be non-parallel and non-intersecting, and usually at right angles, you may realize the internal arrangement. And the advantage, apart from transmitting the torques from one side to the other, is that you may have very high gear ratios, and that is very good advantage to have. Because generally what happens is that for the spur gears, if you need to have high gear ratios, you probably need a compound gear train for that. You need to have multiple spur gears lined up in a housing in order to establish that. But in case of worm gears, you may have simply structured that, and this has got all the flexibility to impart high gear ratios. The other advantage is that it is going to be usually self-locking. What does that mean? It means that you can provide the input on this side and you are going to get the output from this side. But if you try to rotate from the output shaft, the input shaft is not going to have a rotation because of the structure of the worm gears. And that is one very good example, especially in case of motorized control. Uh, this can be very advantageous because you can allow the motor to have momentarily powered off, and the worm gear itself is going to have some sort of locking arrangement, uh, kind of a fail-safe arrangement, if I may say that, imparted. So that is like a question that you have to explore further. I've just raised this question over here, that what is going to be the advantage of worm drive that it offers for the motorized actuators. You need to kind of see what happens when you turn the motor on or off, or when there is something like an overload condition on the motor, what happens over there. So with this realization that we have covered the four basic types of the gears, the first one being the spur gears, then the helical gears, and then the bevel gears, and now the worm gears, we can kind of assure ourselves that we have quite a wide spectrum in front of us to choose from, depending upon the advantages and the disadvantages one particular option may offer. Uh, we can kind of feel confident because of that. You may have other types of gears as well. One example is that of non-circular gears. It is being displayed over here. I can assume the input is being provided on this side and output is being provided on this side. Alternatively, you can have the input on the upper and output on the lower side as well. But just like for the sake of assumption, I can start with that. And you can see that from this point all the way to this point, it gets engaged with on the output side in this arc. And in this arc, the velocity is going to be differently structured, differently exhibited as compared to the other arc. From this all the way to this side, you may have an engagement on this profile. And obviously you can see that you have different velocities at display at different stages of the rotation on the input side. And by the way, this is just like one shape. You can have, depending upon the type of output motion that you require, you can kind of have complex shapes and complex profiles constructed. Another example is that of timing belt or synchronous belts. And that's at display right over here. I can assume that input is coming in from this side and output is from that side. And similarly, you can kind of change the roles over here alternatively. But if the input is coming in from this, you can see that there is a relatively larger distance from the axis of this input sprocket all the way to the output. So this distance is significant. So there is one way of placing multiple gears in this distance uh, uh, to reach to the output shaft. But alternatively, what you can do, you can place a timing belt or a synchronous belt in it. And this belt, if you can observe, there are teeth over here, and these teeth are going to be engaged with the gears on either side. So this is one very good way of transmitting uh, the torques from one side to the other side and reduce the speeds if it is needed, as exhibited by the input and output designations. So this is also very common type of application. And there can be some other interesting gear types as well. Probably you can visit the mechanics lab and you can see that there are quite a few different very interesting displays available in the lab. You can observe those. So at this particular stage, I would say that we have covered quite a few different types of gears, and this is just like kind of we have broadened the horizon, and we know that there are multiple options in front of us, and it depends eventually that what kind of output action that you require, at what axis you require, at what angle you would desire that, in order to identify how the input is going to be transformed into the output to choose the specific kind of gears. So we'll stop over here for in case of gear types, and then we're going to shift on to the other aspect of understanding the necessary terminologies. So before we start designing the gear trains, it would be necessary to understand a few important terminologies. So this is going to be the subsequent discussion. So the very first start or starting point would be from the rolling cylinders example. And you can see that one appeared over here. You have a cylinder, which is the upper cylinder, shown in lighter shaded gray over here. And you can also see that the cylinder has got the rotational direction indicated as well. There is another cylinder which is uh, in contact with the upper cylinder, smaller diameter cylinder, over here. So this contact is ensured at this particular point. Uh, and since the input is going to try to force the lower cylinder to have a rotation, so we can, using our common sense, visualize that the direction of the rotation of the lower cylinder is going to be reversed. And that's going to be a very necessary condition to follow. Whenever you have external set of cylinders mating with each other and rotating, the direction is going to be reversed. So the upper one is going to have a rotation which is counterclockwise rotation, and the lower one is going to have a rotation which is the clockwise rotation. So always remember that whenever you are going to have rolling cylinders or rolling gears, especially spur gears, you are going to have the direction reversal. But that would not be always the case when you have the possibility of placing the input cylinder inside the big cylinder, as is indicated right over here in the internal set in sub-diagram B. So you can see that the input cylinder is going in the counterclockwise direction, and since it is engaged with the bigger cylinder at this particular point, which is inside the cylinder, so that's why it is going to try to force the motion in a sense that the upper cylinder also moves in the counterclockwise direction. So always remember that it depends on the arrangement of the cylinders as well as the gears, which is going to make you uh, realize the sense of direction that your gears or the cylinders are going to have. Now at this particular stage, I'll ask you to uh, just realize that the gears are going to have a similar kind of mechanism. But at the same time, you need to realize the condition which is at display over here or over here at the point which is the point of contact. Now the condition is that there is no slip going on whenever you have these rotations over here. No slip over here as well. What does that mean is that whatever is the input motion given to the input cylinder, the lighter shaded gray cylinder, the same uh, rotation is transmitted to the output cylinder. Uh, Although the diameters are different, but since there is no slip condition going on, it means that whatever is being fed to the input cylinder, that is exactly transmitted without any loss to the output cylinder. Now there's this condition is kind of big condition in a sense that when you have big heavy loads to be rotated on the output cylinder, there is a possibility that you don't have sufficient friction at the point of contact over here, necessarily allowing you to transmit the forces. So in other words, in simpler words, there is going to be slip. So how to avoid that? And that's exactly where geared systems are going to play their part. Geared systems are going to allow, because of the nature of their geometry, this assurance that there is no slip going on between the mating cylinders. So that's exactly what we're going to explore in this subsequent slides. Now, before we move on to the geared system, another aspect that we need to account for is the fundamental law of gearing. And that is that the angular velocity ratio is going to remain constant when these two meshing cylinders or two meshing gears are going to have a rotation. What does that mean? It means that the angular velocity multiplied with the radius of that cylinder is going to remain constant. Or in other words, the velocity vector like this, the v, is going to remain constant. So it means that when this one is going to be a constant, Wn, angular velocity on the input side multiplied with the radius of the input cylinder, is going to be equal to angular velocity at the output times the radius of the output cylinder. So this is a very good expression to have, because it is going to allow you to identify that if you provide certain angular velocity on the input cylinder, how that one is going to be transmitted on the output side. And that is being given by the angular velocity ratio, illustrated in terms of mv right over here, which says that it is going to be omega out over omega in, which is going to be equal to plus minus, it depends on the signs over here, to say that it is going to be r in over r out. And since the ratio of the radiuses are also going to be equal to the ratio of diameters as well, so you can extend this expression for the diameters as well. Now in case of torque ratio, this is going to be just like reciprocal of the mv. So mt actually is equal to 1 over mv, because I've already mentioned that when you increase the speed, you are going to reduce the torque, and vice versa. So that's why the expression is going to be reversed. So for that reason, it is going to be omega in over omega out, which is going to be equal to r out over r in, and because the ratios of the radii is going to be equal to the ratio of the diameters, so that can be extended over here as well. So this expression, or these two expressions for the angular velocity ratio and the torque ratio, are going to be the governing factors whenever you're going to have multiple gears engaged with each other, transmitting motion from one side to the other side. One is going to indicate how the angular velocities, how the kinematics is going to be transferred, and the other one is going to indicate how the forces or torques are going to be transferred from one side to the other. So repeating once again the fundamental law of gearing, the angular velocity ratio between two mating gears is going to remain constant throughout the mesh. Moving on. Now, since we have said that the angular velocity ratio is going to remain constant, So that's why we're going to kind of think about the geometry of the gear profile, which is going to allow you to have that kind of uh, fundamental law of gearing fulfilled in terms of velocity and in terms of torque as well. So the tooth shape, in other words, is what is the most critical part. Now, the tooth shape should have the ability to remain engaged with the other meshing gear, but without violating the fundamental law of gearing. And that's where the involute curve is going to play its part. An involute curve, in terms of its definition, is going to be something like you have a string wrapped over a cylinder, just like the way you're visualizing now on this illustration. And a specific point on that illustration is going to indicate uh, that when you try to unwrap this string from that cylinder, what is going to be the path taken by that point. So this path uh, is going to be called the involute curve, and this has got this ability to uh, to engage the other meshing gear so that it fulfills that fundamental law of gearing that we have just mentioned. So the shape is going to be achieved by unwrapping the string from around the cylinder, and it is going to allow you to fulfill the condition of fundamental law of gearing. Now, there are other possibilities as well. For example, you may have these cycloidal profiles as well, but that is not going to be in the scope of this course. So I'm not going to discuss it over here, but there is always a possibility to have that profile taken as well. So in terms of its illustration, once you complete that, this is going to be the base circle as indicated over here. This is going to be the string which is being unwrapped, and the path taken by that particular point is going to be right over here, which is going to have the involute curve profile. Now, when you construct all the teeth and when you try to engage both the gear wheels with each other, this is going to be the illustration of that. And in this particular case, you can see the red line over here, which is going to indicate the base circle of one of the gears. And this red line, dash line, is going to indicate the baseline for the second. And you can see that when input gear is going to get engaged with the output gear, it gets engaged right over here where this dot appears, red dot appears. And as it rotates, it goes all the way along this line, which is going across these two. So this is the line which is going to be the line which is the line of action, if I may say that, along which the transmission is going on. We're going to further elaborate that later on, but at this particular stage you need to realize that the involute curve profile that I've just previously mentioned in the previous slide is going to be the profile followed over here. And this is going to follow this straight line, which eventually is going to be at 90 degrees on the base circle for the input side and 90 degrees over here for the base circle of the output side. In the subsequent discussion, we are going to use a few figures from this source. You're requested to go online, follow this article as well. So I'm adding my description on these figures, but these are going to illustrate the nature of necessary terminologies in order to understand the geared systems. So let's start this discussion. So in this figure, you can assume that there is one input side over here, and this is the output side. Now, on the input side, you can see the base circle indicated as a dotted line. Here it is. And in order to understand the involute profile that I've previously mentioned, you can assume that involute profile is going to start from the base circle, somewhere from the base circle. And this profile This profile over here is the profile which was illustrated in the previous diagram by unwrapping the fixed string wrapped over the base circle. And now, some detail has been subtracted from the geometry of the gear over here, but that's what is uh, extracted during the machining process. This is not the involute profile. This is not the part of the involute profile, but this is added later. It depends uh, on the selection of machining process as well as the clearances required for a specific grade of gear. Now, similarly, on the output side, you can see the involute profile indicated over here, starting from the base circle for the blue gear. Now you can readily see that there is some difference of the involute profile for both the gears, and that is correct. It depends on the radius of the base circle to define exactly what is going to be the involute profile for corresponding circle. Now, but we are not interested in involute profile uh, as per the requirement over here. We are assuming that we have the gears readily available. So we can assume that the gear profile has been already machined. All we are interested in to find out how the velocity and how the uh, torques have been associated with each other. So for that, line of action is going to be an important parameter to understand. Now, in order to find out that line of action, what I would suggest is to draw a line which is tangent to both the base circles. And that is going to start from some point on the base circle for the golden gear and some point on the blue gear on the base circle. And that is the line of action on which the force is going to be transmitted from one gear to the output gear. Uh, and the other thing that you can realize that since it is tangent, so if I draw the radius to that particular point over here, let it be like point A, this is going to make a 90 degrees angle with the line of action. And similarly for the blue gear, this radius line is going to make a 90 degrees angle over here as well. So line of action in nutshell is the line connecting both the base circles in a sense that the line is tangent to both of them. Now, you should also realize that the radius of the base circle number 1 and radius of the base circle 2 are going to be different. These can be selected depending upon the gear ratio. So that's why it is not always like you have the length of this line of action from this point all the way to this point to be constant. This distance can change depending upon the gear ratios. The other thing that you can readily realize is that the force which is being transmitted from the input gear to the output gear is following the same line of action over here. This red arrow is indicating how the force is going to be transmitted from the input side to the output side. Now at this particular stage, what we're going to do is to identify the center to center distance. So this is center number 1, this is center number 2, and between these two, if I just connect them together using a straight line, this is the line of centers. Now when you are going to draw the line of centers, this is going to intersect the line of action that you have previously drawn at point C. And this point C is very important point for us because this is going to be defining the pitch circle. Now, if you draw normal to this line of centers, you are going to have this line constructed, and this angle, which is between the normal line to the line of action, is what we call pressure angle. Although in this illustration it is referred to be like alpha b, but in your book you can also alternatively see that it is being defined as phi. Now this pressure angle is an important parameter because it is going to define the effective way or effectiveness of a torque transmission from one side to the other, and the standardization and the number of teeth all correspond to the pressure angle specification. But at this particular stage, you can see that we are gradually incorporating some necessary terminologies on the diagram so that you can understand that how to construct them and how to realize them. Now, if I just consider that point C, in terminologies, we call this point to be a pitch point. And this pitch point C is going to have the point where hypothetically these two gears are going to be mating with each other or engaged with each other. So the analogy that we made earlier corresponding to rolling cylinders is going to be mapped right over here at pitch point C. You can see, you can assume this dash dot line, which is the pitch circle, operating pitch circle, to be one cylinder, and the operating pitch circle for the blue gear over here as well, also kind of a cylinder, which is engaged exactly at point C. So now, even if we have used the geared profile over here, we can still make the analogy that we made earlier when we discussed the rolling cylinders in earlier discussions. Now, if I just kind of make it simplified, I would say that I'll have the line of centers and I'll have the line of action, which both are going to pass from the pitch point C. And that would be sufficient to say that we have kind of made necessary analogies with the rolling cylinders example. Now, at this particular stage, it would be appropriate how to correlate the pressure angle alpha B with the angles for corresponding input side and the output side. Remember, we said this to be input side and this to be the output side. And if I just see that the radius of the base circle for input gear is going to have a right angle triangle made, which is going to have the same alpha B as the angle over here that was described over here as the pressure angle. And similarly, on the blue triangle as well, you're going to have the same angle over here. And that's because this line and this line over here are parallel lines because of the 90 degrees indicated with the line of action. So the angle over here and the angle over here is going to be equal, and that is going to be exactly the same angle that we have described previously to be the pressure angle. Now, in this particular scenario, if you're asked to find out the length of a particular output gear, provided the pressure angle, the standard pressure angle, you can simply kind of compute these trigonometric expressions, or geometrically you can solve this problem, and that is going to indicate the missing element if needed be. Moving on, at this particular stage, I'll also make you see that sometimes it is going to be important for you to realize the line of contact and the base pitch, the difference between the two. Now, the base pitch actually is starting from this point, contact point, to this contact point over here. So what happens over here in this meshed gears is that whenever you have uh, one gear tooth to be engaged with the other gear wheel, it is going to have a specific point moving over this involute surface. Now this point is going to be moving. Now, when this gets engaged, it means that now you have made contact, and along this direction you can exert a force. But if you have only one point over here, it is not going to be an effective way of force transmission, because maybe the uh, teeth of the gear are going to experience much more larger forces, which may kind of adversely affect the life of the mating gears. So it would be advisable to have another point contact made on the other side, so that you have an effective way of force transmission from one gear to the other. And the engagement on one side and the point which is going to be disengaged on the other side, the distance between the two is going to be called the base pitch. And obviously the line of contact where it starts the meshing process, which ends the meshing process, is going to be or should be larger than the base pitch. So in terms of designing the gears, so PB should be less than the line of contact L. And this is exactly what we have illustrated over here. PB should be less than L as indicated over here. And generally the rule is that epsilon should be something like L over PB, and that should be greater than or equal to 1. And for spur gears, it is the epsilon is generally 1.2. So this is kind of rule of thumb, or a standard way of describing it, which means that L is a bit larger, or 20% larger than the PB or the base pitch. To sum it up, we can say that we have cleared all the necessary terminologies illustrated on this diagram. So I could have started from this diagram, and I could have kind of started describing all the terminologies, but that would be kind of cumbersome process, because there's quite a lot which is going in this particular figure. So I thought that I'll go in a stepwise fashion, and that's exactly what we have done in the previous slides. So now I'll ask you to consider what is happening, and that should not be a big problem. So if I say to you that, can we identify the origin of one of the gears, I can say that this is going to be OG and OP. The distance between the two is going to be the total distance between the centers. I can find out that. So line of action, or which is also called axis of transmission, is the line which is going to be tangent on the base circle on one of the gears, and tangent to the other side as well. So this line from this to this is going to be, and if I use the highlighter, this is going to be the axis of transmission, or line of action, according to our previous discussion. So it crosses, this line crosses the line of centers at this point, which is called the pitch point. All right, so this pitch point, if you just take the common normal to that, as is indicated by this line over here, this is going to make an angle. This angle is illustrated to be the pressure angle. Now this is going to be the same angle which is appearing over here as well as over here. So now you know what are the centers. what is the center line, what is going to be the axis of transmission or line of action, what is going to be the pressure angle, and what is going to be the common tangent to these. And as a result of that, you know almost all the necessary terminology. Now, on top of that, you can see some terminologies which are kind of alien terminologies, like addendum over here or over here. So this is not like a very complex terminology, in fact. So the space between or the distance between the base circle, like over here, and the pitch circle is going to be indicated to be the addendum of a particular gear profile. So with this realization that you have now the necessary contact geometry also cleared, we can move on. Now, we can once again reiterate the fundamental law of gearing, but now when we are going to do that, we're going to use a more refined definition of it. So it says that the common normal of the tooth profiles, which is going to be this line, the common normal. So the common normal of the tooth profiles at all the contact points within the mesh must always pass through a fixed point on the line of centers. So this is the line of centers, and this is the previous line that we have mentioned it to be common normal. So they must pass through, always pass through, should I say, through a fixed point, what we are going to call the pitch point. So that's the fundamental law of gearing. It must all pass through, always, through the same point C. And that's the fundamental law of gearing, fulfilling all the terminologies that we have mentioned. Now, I've previously mentioned that we're going to have the distance between the two centers to be kind of fixed, but actually it is not. You can change this distance a little bit. So if you change that, if you just observe that it was from this point to this point in the first case, but in the second case, what we have done, we have just shifted the point a little bit upwards. So that difference is illustrated over here, which is the shift in center distance. Now, when we do that, actually what happens is that the tangent line or the common normal is going to pass through the pitch point at a different angle. So this is going to make an angle, a pressure angle, to be a bit different, a bit bigger in precise terms, as was the case previously. So in this case, you can see in the example that we have drawn, the pressure angle was equal to 20 degrees, but when you have increased the center to center distance a little bit, obviously it makes sense that this pressure angle is going to be a bit larger. So when you have a pressure angle to be a bit larger, it means that the transmission of forces is going to be done or carried out in a bit of different fashion. Whether it is advisable or not, that is going to be generally the challenge in front of the design engineers, and the standards are going to illustrate quite a few set of rules in order to allow someone to kind of choose the appropriate pressure angles. But at this particular stage, I would say that you can change this pressure angle a little bit, not too much, but that is going to have an effect on how you transmit the force from one gear. There is one problem with the geared system, and that is what we call backlash. It corresponds to the clearance between the mating teeth. So whenever there is this direction change, you are going to have some no motion phase, which is going to be problemsome. When input is being provided and there is no output being experienced for a little bit of time, that is what we call backlash error. And that is going to cause an error in position. So you're going to expect that the output is at a particular angular orientation, but actually it would not be over there. So you need to kind of avoid that, and that is avoided by having good materials, a good profile carved out uh, of the material, and then possibly have the anti-backlash gears or anti-backlash arrangements incorporated in the gears. So let's shift our focus from two-dimensional description to a three-dimensional description. There are going to be a few terminologies that we have not yet cleared, so let's quickly cover those. So the very first thing that you can start observing is this base circle, which corresponds to this line. And then there is a pitch circle, and we have defined the pitch point, which is uh, going to remain engaged uh, throughout the movement of this mating gear sets. So this is corresponding to pitch circle. Now, if you can see that the distance between the pitch circle and the base circle is defined as the dedendum. Although there are going to be a few clearances involved with that, but we are not going to get into that detail at the moment. But the dedendum in simplistic terms is going to be the distance between the base circle and the pitch circle. And if there are clearances, then you can kind of account for those as well. Addendum, on the other side, is going to be the distance above the pitch circle, uh, but between the pitch circle and the addendum circle being highlighted over here. So these are the two kind of distinctive terminologies corresponding to what is above the pitch circle and what is below the pitch circle, being called addendum and dedendum respectively. And obviously there are going to be some other terminologies. For example, the top land is this area, which is flattened area on top of the gear profile. The face is going to be this surface. Let me use a bit different color over here, this surface. This is going to be the face. And then the face width is going to be depending upon the width of the tooth profile. You're going to define that dimension with that. And similarly, you can see the space width being indicated or highlighted between the point over here to the point over here, in between this valley. And then you can have the tooth thickness similarly defined between the previous point over here all the way to this point on the pitch circle, which is the tooth thickness. So these are a few additional terminologies that are important for you to understand. Now, out of those, if I just define the formula for those, you can see that the circular pitch is being defined in terms of formula like this. It says that the pitch circle is equal to pi times the diameter divided by the number of teeth. So this n corresponds to number of teeth. The diametric pitch, similarly, is going to be a related formula which says that PD is going to be equal to n over d, or in other words, if we define the pitch circle as well, so this is going to be pi over PC, or the pitch circle. There is another terminology which is commonly used, what we call module. Module is just like a number which is defined like with diameter divided by the number of teeth. So this is going to be the module number. Generally what happens is that when you choose specific gears, you just specify the module as well as the standard it corresponds to in order to select those. So this is something like an additional gear tooth nomenclature that you need to clear before we discuss the gear trains later on. There are two more terminologies that you need to be clear about. That is interference and undercutting. When I say interference, it means that the pinion has got too few teeth. So that is the situation when pinion is going to have a movement and it is going to try to move the gear, but since it has got not those many teeth in it, so the effective transmission of forces is not going to be guaranteed. So you need to avoid interference. And similarly, undercutting is also a problem, but that corresponds to the selected pressure angle. So phi is the pressure angle. If you choose this to be, let's say 14.5, which allows you to kind of transmit uh, the forces at this particular angle, as we have previously described, you need to have the minimum number of teeth to be 32 in order to uh, ensure that. So if you have more than those teeth, then you need to provide the provision in the machining arrangement in order to allow no undercutting. So that situation is illustrated over here in this patch, red patch, in this space, in this space. So what happens is that for a selected pressure angle, you need to make sure that how many number of teeth are there in order to be avoiding the undercutting problem. Now I'm going to, at this particular stage, uh, allow you to or invite you to consider the machining processes as well, which allow you to have uh, the the gears manufactured. So generally what you do is like you use the milling machines. There are different kinds of milling machines that can be used, but generally what happens in a manual operation is that you have a dividing head mounted on those milling machines, and this dividing head is going to specify uh, the type of tool engagement with the workpiece, which is going to allow a special kind of uh, gear profile to be machined. For spur gears, it becomes not that uh, cumbersome, but for complex gears, it is going to become a bit difficult or a skill to master. In case of CNC milling machines, it is just like you select a specific command for that, and it in a cyclic operation generally performs the machining operation. So that can be an alternate method, CNC machining. There is another special kind of machine which is called gear shaper machine that is also generally used. This is also in most of these cases semi-automatic machine. What happens is that you have the gear machined using a tool which is also gear-like, and in a controlled machining action, in an iterative action, in a repeated action, it incrementally removes the material, and it allows um, the uh, the machine to perform this increments in a careful fashion in order to shape the gear profile, the involute gear profile. So generally these are the machines which are used for the machining, but once you have the gears manufactured, what you need to do is to improve the surface profile of those. So in order to have the surface profile improved later on after this process, you perform for example, the grinding operation. There are special purpose grinding machines to grind the gear profiles. There is alternatively uh, called a shaver machine or a gear shaver machine. What happens is that you have a very sharp shaver tool mounted on this machine, and it removes the fine material um, on the flanks of these gear profiles. So these are a few alternate options, and once you perform these two super finishing operations, what happens is that you remove or reduce the noise, or you reduce the vibrations as well if you perform these operations as well. So you can kind of explore the machining process as well, so that you have a better understanding of how to manufacture these gear profiles. So with this realization that we have covered quite a few basics today corresponding to the geared mechanisms, we are going to invite you to raise some questions corresponding to the terminologies that we have mentioned in much more detail today. But I'm confident that by going through these set of slides and by going through this video, you will be able to understand and you will be able to comprehend the basic terminologies that would be needed for the subsequent discussions on gear trains. We have not discussed the gear trains today. We will do that next week, but before then you have to revise and repeat uh, the literature and read the literature, follow the instructions that I've given during this presentation in order to see what is needed to be comprehended, what is needed to be understood before we start our discussion on gear trains. So by then, I'll say bye-bye.